All right, our learning target for this section is interpret the Bohr energy level diagram of the hydrogen atom to relate absorption and emission of a particular wavelength to a specific transition between energy levels. What does that mean? Well, it means we're going to look at this Bohr model for the hydrogen atom, which is on the last page of your reference tables. In fact, it takes up the whole of the last page of the reference table. So there's a lot here. Let's identify things on here that we've learned about in this lesson. So we've got lines with arrows. Okay, lines, these are actually circular lines with arrows going from one to another. See these arrows? These are circles. In the talk, we had lines on an energy diagram. So these arrows could represent changes in energy where the system absorbs or emits a photon. Which do you think this is, absorbing or emitting? We need to know if these arrows are going from lower to higher energy or higher to lower energy. Now remember before, when we were looking at all the electrons in an atom, atoms with more than one electron, we said the electrons that were further out were higher in energy. We said that when things are attracted together, like an electron and a nucleus, you need to put energy in to pull them farther apart. So that would say that the one closest to the nucleus is lowest in energy, and then energy would have to be put in to go here, more energy to go here, more energy to go here. The further out you go, the more energy is needed. So these arrows going inward would mean that the energy of the electron is decreasing. So that would mean that this is the lowest, this is the next lowest, and the energy levels are going up. So the energy of the electron is decreasing, and so it must be emitting a photon. So the larger circles we think are higher energy, the smaller ones are lower energy. Now, what is this thing below the atom here? It's got three different sections like Neapolitan ice cream. They're little lines connecting to the arrows, and they have number labels. So these three sections, if you look down, are labeled IR, that's for infrared, visible, and UV. Here's your key saying UV is ultraviolet, IR is infrared. And there are four lines connected to arrows in the visible section. That should look familiar. Remember the four lines in the visible region of the hydrogen spectrum? So this has got to be the spectrum of hydrogen referenced to the transitions between energy levels. Let's look back up and see how Bohr thought those energies were arranged. The longest arrows and the highest energies corresponding, they're here in the UV. Ultraviolet is higher energy than visible or infrared. So that means high energy photons, meaning big gaps between the energies. So the longest arrows all go with transitions from higher numbers to n equals 1. N equals 1 seems to be the lowest possible, nothing below that. Chemists have a name for the lowest energy possible arrangement of an atom. It's called the ground state. So anytime the electron is at level n equals 1, the atom is in its ground state, or we could say the electron is in its ground state. If the electron is in any other state, n equals 2 or above, it is not in the ground state. We are say it is in an excited state, a state that has energy added to it relative to the ground state. Now these transitions from higher up to n equals 2 all match up with lines in the visible. So this must be the visible light we see coming from a hydrogen discharge tube, these four colors. The numbers below them are wavelengths. At the top it says measurements are in nanometers. Okay, so the units are nanometers, that's 10 to the minus 9 meters. They're small. So the red line, which you might remember, was 656, and then two kind of turquoise 486, and two not too easy to see bluish violet ones 434 and 410. Then there's some short arrows here matching lines in the infrared part of the spectrum. Infrared is lower energy, short arrows are lower energy. These wavelengths are longer. We've got 4-digit wavelengths here. Now, if we scroll down, here at the bottom of the page is a representation of the electromagnetic spectrum we learned about. This time, wavelength is in meters. Okay, part of this is the same thing that's represented up here, but higher up, it's nanometers, 10 to the minus 9 meters. Here, it's in meters. Okay, look, here's where visible light fits in between infrared and ultraviolet. And down below, they show kind of an expanded view of the visible. They list the colors left to right in increasing order of energy: red, orange, yellow, green, blue, violet. And at the very bottom, they show the wavelength boundaries for each color. So red is in between 7.0 times 10 to the minus 7 and 6.5 times 10 to the minus 7. Blue is in between 4.9 times 10 to the minus 7 and 4.2 times 10 to the minus 7 meters. So see where all visible light actually fits into a small region of the spectrum in between all those others. Now let's look at the whole spectrum. On the left, the low energy side, we have radio waves. And it shows they have wavelengths of 10 to the fourth, that's 10,000 meters, down to about 1 meter. 10 to the 0 is 1. Then microwaves. These carry your cell phone signal as well as heating your food. Then infrared, which we often think of as heat radiation. It's also used as imaging by military and security. This is how they can see, they can image, they can't see, they can image people at night by their heat signatures. Okay, then the visible. Then ultraviolet, which is higher energy than visible. Ultraviolet A and B from the sun get through our atmosphere and can cause sunburn and skin cancer. But UVB also stimulates our skin to make vitamin D, which is needed for a healthy immune system and protection against viruses. Okay, then come X-rays, which are used in medical imaging. And then gamma rays, which, as we saw in the previous unit, can be emitted by radioactive nuclei. The sun gives off all of these, but only some make it through the atmosphere. Note, longer wavelength, lower energies on the left, shorter wavelength, higher energies on the right. Some people do the spectrum the other way around. Some will express the spectrum in terms of frequency instead of wavelength, but you will always see these same segments with visible light in the middle, infrared on the lower energy side, ultraviolet on the high energy side. All right, sample problems. Let's scroll back to the atom here. If a Bohr hydrogen atom emitted an infrared photon of wavelength 1,282 nanometers, what happens to its electron? All right, so they're giving us a wavelength. We're going to find that on the spectrum. Okay, these numbers are wavelengths. Here's 1,282. So let's connect this to the diagram and see what happens. We have an arrow going from the second outer ring, that's n equals 5, to the 1, 2 down from it. So that's going to be n equals 3. So the electron had to be in the n equals 5 energy level, and it fell in energy back to the n equals 3 energy level, and it emitted a photon of 1,282 nanometers. Okay, next question. What would have to happen to make the electron in a Bohr hydrogen atom jump from the n equals 2 level to n equals 5? Now we're using the term jump, meaning the electron has to increase in energy. If energy is conserved, if the electron goes up in energy, then energy has to come into the system. So here's n equals 2, here's n equals 5. So jump means go from 2 to 5. Energy's got to come in. That means a photon has got to be absorbed. So here is an arrow between 2 and 5. Now it's going the wrong way because it corresponds to the electron dropping from 5 to 2. But we can easily see from 2 to 5, it's the same energy distance. And the photon that would be absorbed to make this happen is if we connect the line down here at 434 nanometers. So that's basically how you read the Bohr electron diagram, and I have left some problems for you to answer. I hope you will be well equipped to answer them.